Okay, so buckle up here because there's a lot to get through. So looking at this first function here, we want to find the derivative. And I like the first step that you did. You distributed the x. That's a good call. I'm going to go ahead and write it like this with your permission. And what I'll do now is I'll take the derivative term by term. So f prime equals the derivative of x is just 1. Now, you see how when I distribute that to that, that's really 4x, but I put out the constant 4 to the front, the coefficient. I want it just to be x's here. Because what I'm going to do is I'm going to keep the 4. And in here, I need the derivative of that. So we hit this with the quotient rule. Bottom times the derivative of the top, which is 1, minus the top times the derivative of the denominator, which is 1, over the bottom squared. And now what we can do, I suppose, is in here, x plus 3 times 1 is just x plus 3 minus x. The x's knock out. So inside, we really just have this left, like that. And let's call this a 12 over this stuff here. Technically, this is the answer. Well, technically, this was the answer. It's just a matter of simplification. So what I'm going to do is I'm going to rewrite the 1 as x plus 3 squared over x plus 3 squared. I've essentially gotten a common denominator. Now these are the same, so I can subtract these. But recall that that there is. Okay, so that was f prime of x. It was a matter of cleaning up this mess, right? We got the derivative right away, but then we have to do all this algebra to get this here. Now for the next one, we want to model this. So we have a rectangle, and we're given that the length is 6t plus 5, and the height is this here. And we want to know the rate of change of the area with respect to time. So area is base times height, or length times width. And you can distribute if you want. That would be easier. That'd be 6t to the 3 halves plus 5t to the 1 half. Recall that square root t is the same as t to the 1 half. And remember that there's a 1 right here. So when you distribute these, you have to add the exponents. So 1 plus 1 half is the 3 halves. That's there. And now we want the derivative, so we can go term by term differentiation. So power rule, that times that is 9. Subtract 1 from that is 1 half. And then that times that is 5 halves. Subtract 1 from a half, it's negative 1 half. With your permission, I will do this instead. I will make that positive by dropping it to the bottom, but while I did so, I changed it from exponential form, from a rational exponent to a radical. And now we know that there's a 1 here, but we want to get a common denominator because I want to have two things into one. So I multiply by 2 square root t. 2 square root t. That'll be 18t plus 5 over 2 square root t. I believe that's the finished result. So 9 times 2 is 18. Square root is t. That's just 5. Common denominator established. And here it was centimeters times centimeters, so it's square centimeters. That's an area dimension, square units. But that's how quickly the area changes with respect to time in seconds. And for this one, we want the derivative. So I have bracket x squared plus 3 close to the 5th plus x bracket 2. So we want the derivative. And I would apply the power rule. So the 2 goes to the front, and the 2 becomes a 1. Everything inside stays the same for now. You want to do this chain rule by peeling off one layer at a time. The outermost layer was the power rule, 2, boom, subtract 1, boom, stays the same. But now I multiply by the derivative of the inside, the original inside. Well, let's take the derivative of this and then the derivative of that. Let me open this up. Just in case there's a lot of pieces that get created, I want to keep them in parentheses. So this derivative, well, do the 5. The 5 becomes a 4. The inside stays. But then I multiply by 2x because the 2x is the derivative of the inside. You see how it's so embedded? So that derivative is there, plus 1, close this. And let's see, why don't we, I think they want us to clean this up. So why don't we distribute the 2, and let's see, so this is 2 parentheses x squared plus 3 to the 5th plus 2x. And so I've distributed the 2, but it's still in parentheses because it's times. And 5 and 2x, that's 10x with x squared plus 3 to the 4th plus 1. And now let's apply the distributive property. Sometimes they call it FOIL, but it's really called the distributive property. And let's do this carefully. So we have that times that. That's going to be 20x. And ooh, look, these puzzle pieces match. It's the same stuff, but that's a 4, that's a 5. 5 and a 4. So you add the exponents together. And then this times that is just that. And let's see, so now the inside, that times that, would be positive 20x squared with this piece here, plus 2x. So this looks to be the case. I don't think we have any like terms from here, so that represents our derivative. And now let's try this one here. G of x equals 5 tangent of 3x. We want the derivative. So let's see. So the 5 just chills there. The derivative of tangent is secant squared of stuff, where the stuff is the original stuff. But then you multiply by the derivative of the inside, which is 3. So that's just going to be 15 secant squared 3x. So again, this has a chain. The outer shell is tangent, and then the inner shell is 3x. The derivative of tangent is that. So you preserve that for now, but then you multiply by the derivative of the argument, which is 3. They call this the argument. I could have put parentheses around there, doesn't really matter, but there's your derivative. Let's try the next one here. So we have f of theta, a quarter times sine squared of 2 theta. I put parentheses there. What I'll also do, before I do any calculus, I am gonna do algebra. I'm gonna rewrite that as that. I think it's way better if you look at it like that, because then I can apply the power rule. So now f prime of theta would be 1/2, and this stays the same, 2 theta, and that's a 1. So 2 times the 4th is a half, 1 times the derivative of this. So the derivative of sine is cosine. So the derivative of sine is that. You preserve that, but then you multiply by the derivative of 2 theta, which is just 2. 2 knocks out the half, so it's essentially sine 2 theta, cosine 2 theta. And I know that, look, this is correct, but that's not how they have it. Let me show you what they did. So let me just do some scratch work down here. Remember from honors pre-calc that sine of 2 theta equals 2 sine theta cosine theta. Now let me do this actually. Let me write this a different way. Let me write this as sine 2, and then I'm going to put box equals 2 sine box cosine box, so that whatever is in the box goes here, here, and there. And what I'm trying to, I want to go from right to left. Now, if you look at what you have, this is our answer. And I want to use this to get their answer. But notice how here there's a 2, but yours doesn't have a 2. So what I'm going to do, I'm going to divide this formula by 2. So these are gone. So this says that 1/2 sine of 2 box equals sine box cosine box. And the reason I've done it is because now ours looks just like theirs. So you see, this is an identity. And what you have is on the right, is here. They want to be on the left, there. So watch what we do. Sine box, sine, that's your box. Cosine box, cosine, that's your box. So on this side, I need a 1/2 sine 2 times box. 2 times, now what's playing the role of the little box? 2 theta. And of course, 2 times 2 theta is 4 theta, which is why they got 1/2 sine of 4 theta. Did you have to do this little manipulation? No. It's kind of annoying that they made us do that, but we did it. Okay, now we have h of x equals sine of 2x times the cosine of 2x, and we want the derivative, so we'll hit this with the product rule. So I like to call this f, and I'll call this g. And I know that for the product, f g prime plus f prime g. It's always f g, you switch the derivatives to either one. So just give them this. The order doesn't matter because it's addition, which commutes. So just give them this here, and that'll be it. So you can also do, what I tell students sometimes is to do this. So f is that one, g is that one. And what would be f prime? The derivative of that is cosine 2x times 2. The derivative of that is negative sine 2x times 2. And now take f prime, g prime, build this, put it there, and you're done. So let me just write it down here. I don't have enough space. So f g prime, so I need this and that. So f and g prime would be negative 2 sine squared 2x, because the negative 2, sine 2x, that's sine squared 2x, plus, and then f prime g would be these ones. So that'll be 2 cosine squared 2x. And then what you can do here is, let's reverse the order. So this is 2 cosine squared 2x minus 2 sine squared 2x. You can factor out a 2 so that it's cosine squared 2x minus sine squared 2x. And then use the identity. There's an identity that says here in blue, it says cosine squared box minus sine squared box equals cosine of 2 times box. And let's see, what we have here looks a lot like this. So let's see if we can piece this together. So that 2 is just chilling. But all of this, which is that, needs to get replaced by something that looks like this. So see, cosine squared, box is 2x. So here that'd be cosine, parentheses, 2 times box, but box is 2x. So this is 2 cosine of 4x. So it was a lot like the previous one, and there it is. So up next, y equals ln e to the x squared, and I believe we want the derivative. So let's see, let's call this y prime. And oh, you know, now that I thought about it, let's go back to the one that had to do with this one here. So instead of a, it should have been like dA dt, right? The derivative of area with respect to time. So anyways, back here, y prime, well, the derivative of natural log, recall that the d dx of ln of x equals 1 over x dx. So you reciprocate that thingy. So here, the first step is to reciprocate this argument. So it's 1 over e to the x squared times the derivative of the inner part. So the question is, what is the derivative of e to the x squared? Well, the derivative of e to the whatever is itself times the derivative of the exponent, which is 2x. And this is, well, that's gone. That's nice. So it's just 2x. So just FYI, let's say you have e to the 5x squared. And what would be the derivative of that? Well, copy and paste, and then you multiply by the derivative of the exponent, which is 10x, just FYI. All right, let's keep going here. Here is what I would do. I would use algebra before I use any calculus. So the square root is the same as the power of 1/2. And then recall from earlier math classes that for a logarithmic expression, you can place any exponent on the argument to the front. And now I will take a derivative. So now it's y prime equals 1/2. Well, the derivative of ln is you take this and you reciprocate it. So it's 1 over that. And there's a shortcut to this, but I'll just be proper. So 1/2 is there. ln, I turn this upside down, there it is, times the derivative of that. Well, that's a quotient rule. So let's just focus on the derivative of that quotient rule. Bottom times the derivative of the top, which is 1, minus the top, in parentheses, times the derivative of the bottom, which is 1, over the bottom squared equals 1/2. If you have 1 over a fraction, it's just the reciprocal of that fraction. It's a pro tip. See that? I just turned this upside down because it was below 1 times. Up here, if you distribute, that's just going to be x minus 1 minus x minus, distribute that negative. You see that negative 1? Distribute it to both. Those are gone. It's just negative 2 over x minus 1 squared. And what's nice is that 2 knocks this out, so it's just negative 1. So what's left? I have a negative. That negative 1 is there. It's invisible. That's up there. In the bottom, I have x plus 1. And then I have x minus 1, because square means 2 of them. So this knocks this out. So I have negative 1 over x plus 1, x minus 1. I think that they distributed. They used the distributive property. So it's negative 1 over x squared minus 1. But what you can do is you can kick the negative down to the bottom. So it's negative x squared minus 1. And then distribute the negative to get 1 over 1 minus x squared. So again, more algebra. And that's the result right there. Squared, I want the derivative. I could go quotient rule, but well, watch this instead. I'm doing this just to show you different options that you have. So I could just bring it upstairs and make the power negative. So that now it's just a power rule. If I go derivative, now it's just a power rule instead of a quotient rule. So that times that is that, keep it, subtract 1, keep it, times the derivative of the inside, which is just 1. So the derivative here would be negative 16 over the cube of that difference. X squared minus 1 over x. And we want the derivative. Now, look. The derivative for log, if you have log base a of x, d dx would be 1 over x ln of a. And there are many ways of doing this. You could use log properties to expand this and go term by term differentiation. I'm just going to apply this property. So y prime equals, based on this rule, it's 1 over x is that thingy right there, like that, times ln of a. Natural log a is the base, which is 10. So that's my setup. And if I clean this up, it's really just going to be x over x squared minus 1 times the natural log of 10. That's really as clean as it gets. I mean, I know that they want us to clean this up a lot, but that's a totally fine answer. I mean, I could do some things to it, but I'm just going to call this the answer for that one. And this was the answer here. And here we have a piecewise defined function, and they want us to tell them whether or not this function is differentiable at the location x equals 1. So a quick FYI, something like this is differentiable everywhere except here. This is no good. Now, it is continuous, right? It's continuous, and that's one requirement. However, the other requirement is that at any point, the slope of your tangent line coming in from both sides has to be smooth and steady and gradual. You see how if I approach this number from the left, my slope is negative, the tangent line, and then suddenly it goes to a positive slope. There's no smooth, gradual transition. The derivative goes from a negative to an abrupt positive, as opposed to something like this. Here, it's first of all continuous, but also look at the slopes. The slopes of these tangents are slowly getting close to 0 from both directions. So that's why this would be differentiable and this one no. So there's really 2 steps to see if this is differentiable. First of all, it has to be continuous. So for continuous, plug in 1 into this, plug in 1 into that. If I plug in 1 into here for x, 2 minus 1 is 1. That's the y. That's the top part. Now the bottom part. Plug in 1 for x here, and 1 squared minus 2 plus 2 is 1. So is this continuous? It is. This is continuous at x equals 1. So for continuity, plug in whatever number this is into both parts, and it has to have the same output. If these are different, then no, tell them nope, not differentiable. However, if it is continuous, you got to keep going. And for that, you find the derivative. And you keep everything the same. I found the derivative of this. I found the derivative of that. And then plug in 1 again, and the derivative has to equal. If I plug in 1 into there, that slope, the slope for this one, if I plug it in, is just -1. If I plug in 1 in there, it'd be 2 minus 2, which is 0. Ooh, these slopes are not the same. So does not equal 0. So nope, not differentiable. If you were to graph that, what would that look like? That would look something like 2 minus x. So we have 1, 1, and something like that. 2 minus x, it would look something like this here. And for that, that's a parabola at 1, 1. It's probably going to look, I mean, I'm not exactly sure. It's going to look something like that, right? Where it's continuous, but on one side, the slopes are fixed. But from the other side, the slopes are gradually getting closer to 0, but it's not smooth. It's like herky-jerky. See, that's what you call a corner. And I'm not sure if this is called a corner or not, but this is not differentiable. So you have to be continuous by plugging this number into both parts to get the same output. And it has to have a smooth transition with your slopes, where the derivative, you plug this number into both parts, and it has to be the same number. And if it is, then it would be differentiable. But let's see what this looks like here. So I'm going to plug in -1 into there. So that'd be -1, 1, and that's going to be open. And that would look something like that. And then from -1 to 1, if I plug -1, it's 1. So that's going to make it, that's going to fill it in actually. So this part filled in the hole from the previous part. And if I plug in 1 in there, it's 1, 1. It's going to be a parabola. The parent function looks something like this. And then from there, I look like x. So this would be open from here. That would be an open circle, but it's filled in by that part. So this graph looks something like this. Piecewise defined function. And they want us to tell them, where is it differentiable? Give a formula for g prime. So g prime, the derivative. Give them all the constraints. So here was the graph of g prime. And let's see, so I want to know, I can see that g is continuous. It's continuous, so that part's good. But I need to know if it's also differentiable by checking the slopes. So we go to g prime. So we go to the derivative. And -1, -1. Plug -1 into there, you get -2. Plug -1 into there, you get -2. And you can even see it. I mean, I'm not an artist, but it's actually quite smooth. You see that? It's smooth there. So that's why I said yes, differentiable there. And for sure it's differentiable at everything in between. It's differentiable everywhere before, and it's differentiable everywhere after. The question is it differentiable at 1? So you go to the derivative, you plug 1, 1 into here. If I plug 1 in there, it's 2. Plug 1 in there, it's 1. They're not equal. So no. So it's differentiable everywhere except at 1, which is what that's saying. It's differentiable for all real numbers except for 1. So there you are. I hope that helped. And feel free to send me any more problems that you have. So nice job. Keep working hard, and I'll talk to you next time.